So, in order to understand or realize the simple gas laws, namely the relationships between temperature and pressure and moles, which are symbolized with a small case n, or volume, all we really need to do is take a look at what pressure is. And we learned on the last video that pressure equals the ratio of the force exerted by the particles as they hit the container walls to the surface area of those container walls. And so anything that increases the force of the particles would increase the pressure, and anything that increased the surface area of the container would actually decrease the pressure. There's a relationship here that's indirect, and a relationship here between force and pressure that's direct. Now, in order to understand how these four quantities play into this concept, you have to realize that really the force of the gas particles depends on two things. First, it depends on how many moles of gas you have. For instance, if I put more moles of gas into a container, there will be more collisions with the container sides, creating more force. Likewise, if we increase the temperature, of course, temperature measures kinetic energy, and the higher the temperature, the faster the particles are moving when they slam into the container wall, and that also increases their force. So adding gas or heating the gas would increase the pressure of the gas. Likewise, removing particles of gas or cooling the gas would decrease the force and decrease the pressure. Well, we rarely measure the surface area of a container, but instead we measure its volume quite frequently. And of course, volume and surface area are closely related. The larger the volume you make your container, the greater the surface area surrounding the container will be. So this is all of our simple relationships between temperature, pressure, moles, and volume. Instead of thinking as pressure being equal to force over surface area, I instead think it's proportional to the moles of gas and the temperature of the gas, and is inversely proportional to the volume of the container holding the gas. Now, we can use this understanding to do what are called simple gas law problems, which involve changing conditions. For instance, I have a sample of gas, and I give you its pressure, and I give you its volume. And then I change the volume and ask what will happen to the pressure. This is what I call a changing condition problem. And I can solve this easily with an understanding known as Boyle's law. Boyle's law relates pressure and volume of a gas. And I keep remembering that force is a function of temperature in moles, and that volume or surface area is a function of volume. And just thinking this way allows me to see there's an indirect relationship between pressure and volume, namely, whatever change happens to our volume, the inverse change will happen to the pressure. So I start these changing condition problems by writing down the condition I'm asked about, and that would be 3 atmospheres initially. 3 atmospheres, and I want to know what the pressure will be. And then I do a simple proportional change. In this problem, the volume is increasing from 2 to 5 liters. And because pressure and volume are indirectly related, a 2 to 5 increase in volume would result in a 2 to 5 decrease in pressure. So all I do is write the 2 liter volume up here, the 5 liter volume down here. This creates a ratio less than 1. And when I multiply my pressure by this ratio less than 1, I will get the lower pressure I'm expecting. And if I multiply this out, I get 1.2 atmospheres. Yes, by increasing the volume 2.5 times, I have decreased the pressure by 2.5 times. So yes, I do a simple proportional change of one of the conditions using the two conditions I was given to change. How about another problem like that? Well, here's another changing condition problem, because we have a gas and we're given its pressure and we're given its temperature. And then we're asked what will happen to the pressure when we change the temperature. And this is negative 40. The negative didn't go with the 40 for some reason. Now, a key warning is in any gas laws, you have to use temperatures in kelvins. And that's because we're talking about kinetic theory. And there can be no slower particle than a particle that stops moving. There is a lowest possible kinetic energy, 0. And there's a lowest possible temperature, absolute 0. So on the Kelvin scale, motion would cease at 0 kelvins. And so if we're going to talk about motion and pressure and kinetic theory, we have to think in kelvins. So immediately when I see temperatures in a gas law, I convert them to kelvins. And 30 degrees C is equal to 303 kelvins. And negative 40 degrees C is the equivalent of 233 kelvins. So you see, my temperature is really dropping by about 70 300ths. That's about a quarter drop, namely 25% decrease. Now I do the problem the same way. Since it's changing conditions, I would start with the condition I'm asked about, pressure. And the initial pressure was this, 455 millimeters of mercury. And then all I do is adjust the pressure proportionally to the change in temperature. But first I remind myself of the relationship between not pressure and volume in this case, but between pressure and temperature. And that's a direct relationship. As temperature climbs, the particles collide harder with the container wall because they're moving faster, and the pressure would go up. So in this case, if the temperature is decreasing, I want an equal decrease in my pressure. So I'm not going to put the larger over the smaller number. That would give me something greater than 1, and I get a greater pressure. Instead, I put the smaller pressure or temperature over the higher temperature. And the kelvins cancel. And what I'm saying is that my pressure will decrease by this ratio. And that's the same ratio by which the temperature decreased. So I expect an equivalent decrease in my pressure. And when I take my and multiply this out and round to 3 digits, I get 350, but of course with 3 significant digits, I would write it as 3.50 times 10 to the 2 millimeters of mercury. So yes, with a temperature decrease came a pressure decrease, because pressure is directly related to temperature. That, by the way, is called Gay-Lussac's law. Now, here's another changing condition problem, because here I give you the amount of oxygen gas, 2 moles, and I give you its pressure. And then I ask what the pressure will be when you add 3 more moles. And of course, if I add 3 moles to 2 moles, I end up with 5 moles. In other words, be careful. This didn't say that the amount of gas changed from 2 to 3 moles. No, it increased by 3 moles, so it's changing from 2 to 5 moles. I then ask myself, what's the relationship between moles and pressure? And that too is direct. A larger number of molecules will create a larger force against the wall and a higher pressure, and less amount of gas would result in a lower pressure with fewer collisions. So again, if it's changing condition and I'm being asked for pressure, I start with the pressure I'm given, 3.0 atmospheres. I remind myself that the relationship between moles and pressure is direct, and since the moles are increasing from 2 to 5, I want an equivalent increase in the pressure. So I put the 5 over the 2 to give me an increase when I multiply of my pressure. Moles cancel, and I get 7.5 atmospheres of pressure. Of course, we're having a 2.5-fold increase in how much gas is in the container, so we're going to have 2.5 times as much pressure exerted against the container walls. As a final example, using two different conditions, we have a sample of nitrogen. I'm given its volume in cubic inches this time, and its temperature. And we change the temperature and want to know what happens to the volume. Once again, whenever I see a temperature with gas laws, I immediately convert to kelvins. 293 kelvins. I immediately convert the other temperature to 333 kelvins. And then I look for the relationship between temperature and volume. And by the way, this is called Charles' law, this relationship. Now, this is a little bit more problematic because in all previous cases, we were comparing these changes directly to the pressure, either indirectly or directly. And now I'm asking about the relationship between these two. So what I do is I pretend that this is constant, doesn't change, and this is constant, doesn't change. Now, if the temperature in the numerator goes up, the volume in the denominator would also have to go up for us to have the same pressure for our gas. So yes, that is in fact a direct relationship. Things that heat up tend to expand, and things that cool down tend to contract. So it's a direct relationship, really, between temperature and volume. And you could see it if you multiply both sides of this expression by volume. Now I would see that temperature is directly related to volume when I do that. So, solve the problem the same way. We're asked about volume, so I start with the given volume, 2 inches cubed. And I then do a quick conversion. I check the relationship between temperature and volume. It's direct. In this problem, the temperature is increasing, so the volume must increase by the same proportion. So I put the larger temperature over the smaller, such that when I multiply, I will get a proportional increase and not a decrease. And this comes out to a 2.27 cubic inch volume. So yes, by heating our gas up, we saw an increase in our volume. So to do any of these problems, I'm going to do the same thing always. I'm first going to remind myself of the pressure, temperature, volume relationships. I'm going to see what's happening to my condition that's changing, and then I either make the same change proportionally or an indirect change proportionally to that other quantity about which I'm being asked. And that's the easy way to solve all of these. If you don't do it this way, then you have to remember equations. For instance, this is another way to think of Boyle's law as an equation, where the first pressure times the first volume has to equal the second pressure times the second volume. But if you use this equation, you end up having to do algebra to solve for whatever quantity you're asked for. Charles' law, same thing. V1 over T1 equals V2 over T2. And I could have solved this problem right here that involved volume and temperature using this equation, but I would have had to solve for a variable. And if I choose to do it the way that I've just explained, I never have to solve for anything. I'm just taking a condition and creating a ratio out of the condition that's changing to find what change occurs.